Hi, I'm Umang Bhaskar. I'm going to be talking about a problem in fair division, in particular on optimal bounds on the price of fairness for indivisible goods. This is work done with Siddharth Burman at ISC and Nisarg Shah at the University of Toronto. So let's jump into it. So I'm given fair division instance. What this means is that I'm given a set of n agents and m goods. I'm going to be using capital G always to denote the entire set of goods available to me. And the goods are indivisible, which means that a good cannot be divided amongst multiple agents. Right? Every agent either gets the good or she does not. Now, every agent I has a valuation function v sub I, which maps a set of goods to the value she gets if she gets that set. Right? For set S, v sub I of S is the value of agent I for the set S. These valuations are going to be publicly known, so I'm going to ignore any strategic behavior. And there will be a central agency who has to come up with some fair division of the given set of goods. And I'm going to be looking at different classes of valuations. One class that will come up again and again is the additive class, where for a subset S, the valuation of an agent I is going to be the sum of the values that agent I has for all the goods in that subset. So V sub I of S is going to be the sum of all goods J in the set S of V sub I of J. Further, I'm going to say that V sub I, the valuation function V sub I is scaled if the value for the entire set of goods G is equal to 1. I'm also going to be assuming that if an agent doesn't get anything, she has value 0. And secondly, that I'm looking at the case of goods. So the valuation function is monotone, which means that if I assign a good to an agent, her value should not decrease. And given this, I would like to come up with a fair allocation of the set of goods. So before we look at fairness, let's first look at another common objective which is studied, which is the social welfare. So in this case, I want to come up with an allocation A to maximize the sum of values of the agents for the bundles that that she is assigned. Right. So I'm going to be using this A equals A1 through AN to denote an allocation where AI is the set of goods that agent I gets and A1 through AN partition the set of goods. So as I said, this is a very commonly cited objective. We know a lot about this. Let's take a look at a quick example. So for example, let's say over here that the green agent has something in additive valuations. The green agent has value 100 for every good. So the green agent gets k goods. Her value is going to be k times 100. The red agent has value 10 for every good. The blue agent has value 1 for every good. And clearly, the allocation which maximizes the social welfare is going to be assigning everything to the green agent. So we haven't defined fairness yet, but clearly this cannot be very fair, right? We're just completely ignoring the red and the blue agents. So maximizing the social welfare can be very unfair. That said, it is economically efficient. It does maximize the social welfare. A weaker condition, which again will pop up again and again, is that of Pareto optimality, where an allocation, I'm going to say, is Pareto optimal if any other allocation must leave some other agent worse off. So no other allocation can improve the valuation of some agents while leaving the allocation of the other agents unchanged. This is economically efficient, and as I said, this is very well studied. So we know a lot about hardness, about approximation algorithms for various classes of valuation functions, if that is our objective. As we said, this is not fair. So we're going to look at two very well studied common notions of fairness, Envy-Freeness and maximum share guarantee. And these have different perspectives on what they mean for fairness. So Envy-Freeness basically says that no agent should want what another agent has. So an allocation where every agent is satisfied with her own set of goods, she doesn't want what anybody else has. In maximum share, we take a different approach. There may be envy. However, we say that every agent must be getting at least a basic minimum value. We'll define what this basic minimum is. So we'll define all of this. I just want to jump ahead a little bit and say that it turns out that in fact these are very strict properties and they may not even exist. Even for additive valuations, these do not exist. So in fact, we will be looking at relaxations of these. But let's define them first. So I'm going to say that an allocation is envy free If, as I said, no agent envies what any other agent has, which means that for every pair of agents I and j, the value that agent I gets for her own allocation A sub I is at least the valuation that she has for agent j's bundle A sub j. Right? Okay, cool. So this is Envy-Freeness. A simple example to show that this does not exist, consider just two agents and there's one good. Both of them have value 1 for this good. Now, no matter whom you give this good to, there's going to be envy, right? If you give it to the red agent, the green agent is going to envy the red agent. She will want what the red agent has. So we're going to relax this. In particular, what we're going to look at is Envy-Freeness up to one good. What this means is that I'm now allowed to remove a good from J's bundle. Right? So A, allocation A is EF1. If for every pair of agents I and J, there exists a good G in agent J's bundle, so that if I remove this good G, then agent I's value for her own bundle is at least her value for agent J's bundle minus this good. Okay? So I can always remove some good to remove envy. And now, in this simple example, any allocation, in fact, is EF1 because right now, yes, the green agent does envy the red agent. I'm allowed to throw away a good. So if I throw away the strawberry, then both of them have value 0. And, it's fine. There's no envy. Let's take a look at a slightly more interesting example. So there are two agents. They have identical additive valuations, right? So both agents value the strawberry at 10, the eggplant at 6, and so on. And you can stare at it a little bit. This is actually an EF1 allocation. The green agent, envy is the red agent, right? The green agent has value 10 for her own bundle and value 14 for the agent for the red agent's bundle. However, if I remove the eggplant from agent J's bundle, then the value is now just 8, right? Which is less than what the green agent has for her own bundle. So this is EF1. Okay, so what's nice is that EF1 allocations are known to always exist for monotone valuations, right? Additive, subadditive, submodular, what have you. They always exist. In fact, they can be efficiently computed. In fact, what's also known is that at least for the case of additive valuations, we can also find allocations which are EF1 and Pareto optimal. Right? And these are given by maximizing what's called the Nash social welfare. Let me not define that right now. So a number of nice properties for EF1 allocations are known. Right. So we talked about Envy-Freeness, in particular relaxation EF1. Let's talk about MMS. So what is this basic minimum guarantee? So let's fix an agent I. Right? What is the basic minimum that I should guarantee agent I? Well, I have to partition the set of goods in. If there are n agents, I want to come up with an n partition. Let's say that I allow the agent I to pick the n partition. However, she gets the worst part in that partition. Right? In that case, what value can she guarantee herself? Right? So agent gets to pick the partition, however, she always gets the worst partition. Let's take a look at this example. Again, two agents, a single good. The green agent has to come up with the two partitions. So there are two boxes she has to fill. There's only one good. So some box, no matter what she does, is going to have value 0. That is going to be the worst box. So agent I maximum share in this case is just going to be 0. Okay. So if you look at a slightly more interesting example, so now I have three agents and the green agent has additive valuations again. So now she has to fill up three boxes. She has to come up with a three partition. Let's say this is how she partitions it. The worst box has value 6. So her maximum share is going to be at least 6, right? So this may not be the best partition. In fact, this is what the best partition looks like. Now, the least value she can get from any box is 7, and that is her maximum share. Right? So the agent gets to pick the n partition, and then she gets the worst part in that partition. Right. So a maximum share allocation is where every agent gets her maximum share guarantee. Right? So allocation A, V sub I of AI is at least agent I's maximum share guarantee. And again, as we said, this may not exist. These are very complicated examples, but even for additive valuations, we know that this may not exist. So we're going to look at the relaxation. In this case, we look at a multiplicative approximation. So I'm going to say that an allocation is an alpha maximum share allocation if for all agents I, she gets at least alpha times her MMS guarantee. okay, where alpha is something less than 1. In fact, we're going to be looking at the case where alpha equals 1/2. Okay? Every agent must be getting at least half her maximum share penalty. So what's known, so this MMS, in a sense, it generalizes this very well-known protocol for cake cutting between two agents, right? It's called the cut and choose protocol. How do you divide a cake between two agents? Well, what you do is that you let the first agent cut the cake into two parts which she believes are roughly equal, and then you let the second agent decide which one she picks. Right? So the first agent partitions the cake into two, but she may get the worst partition. And so one MMS, as we said, may not exist. However, 3/4 MMS is known to exist for additive valuations. Okay, so these are the two fairness notions we'll be looking at. EF1 and half MMS. I just want to say that there are various other fairness notions which have also been studied: EFX, group-wise maximum share, equitability, and so on. I think these are great candidates for future work. We have not studied this in this work. This is outside our scope. Okay, so I won't talk about them now. Right, but that's our goal. So we want to. So as we said, the social welfare is going to be unfair to maybe unfair to agents. So if we insist on fairness, we want to understand what is the effect on social welfare. And in particular, the way we do this is that we look at this ratio. So given a fairness notion, let's say either EF1 or half MMS, I'm going to be looking at the worst case ratio of the social welfare I could get in the instance ignoring any fairness to the social welfare I get if I insist on fairness, either EF1 or half MMS. Okay? I want to obtain bounds on in the worst case for this ratio. I know that this is at least 1. The numerator is at least what the denominator is. But where does this lie? Right? So that is my goal. So I want to obtain hopefully tight bounds on the price of fairness for EF1 and half MMS for the case of indivisible goods. I want to mention that this price of fairness is motivated by similar to in game theory we study this price of stability, which is roughly the same thing. It looks at the worst case ratio of the social welfare obtainable to social welfare obtainable at an equilibrium. Right? In this case, instead of equilibrium, we're looking at fairness. Okay, so here's what's known about this. We are not the first to study the price of fairness. It's been studied in various contexts earlier. For divisible goods, what's known is that, firstly, it's known that envy-free allocations exist for divisible goods. Right? So we can look at the price of just Envy-Freeness, not EF1. And in this case, it's known that the price of Envy-Freeness is exactly theta square root n. Right? But n, remember, is the number of agents. For the divisible goods, for the indivisible goods setting, what's known is that again, we can look at the price of Envy-Freeness. Envy-free allocations may not always exist, but we can restrict ourselves to instances where it does exist. So for this, it's known that the price of Envy-Freeness is theta of n. If we relax it to EF1, then we don't have a tight bound. So this was studied in this paper by Bay et al. And what they showed was that the price of EF1 lies somewhere between omega of square root n and order of n. They give a lower bound and its upper bound of order of n. They also obtain bounds on the number of other fairness notions, including mass social welfare, Lexi-Min, and so on. And I would say the price of fairness has also been studied in a number of other contexts, including chores, machine scheduling, networking, etc. And so this is by now a fairly well-studied concept. Okay, what's relevant to us is that we prior to our work, we did not have tight bounds on the price of EF1. We have a lower bound of omega of square root n, upper bound of order of n. And in fact, the price of alpha maximum share was not studied at all. So we are the first to study this, and we will give tight bounds. With that, let's jump into our results. So our first result is to give tight bounds on the price of EF1. We show that in fact the lower bound is correct. The price of EF1 is actually theta square root n. We show that this is true in fact for all classes of valuations between additive and subadditive. I haven't defined subadditive, but I'm going to say an allocation is subadditive if, a valuation is subadditive if for any two sets, the valuation of the union is at most the sum of the individual valuations for S and T. Right, and this includes summative, includes submodular, XOS, various other classes of functions. Right, so for this very wide set of classes, we give tight bounds on the price of EF1. I haven't talked about prop one. I don't want to define it in case you know what it is. But additive utilities, in fact, our work also gives tight bounds on prop one as well. What about MMS? So for half MMS, again, we show exactly the same results. We show that the price of half MMS is theta square root n. However, here we restrict ourselves to the case of additive utilities. I should say that for MMS, the case of non-additive submodular sub-additive utilities is less well studied. There are results, but for example, we don't know if a half MMS even exists for submodular utilities. Okay, so for additive utilities, we show the same results. We show theta square root n bound. I should mention that the lower bounds are basically from earlier work. So our contribution is to the upper bounds. All our upper bounds are obtained through polytime construction. Right? So it's constructive, efficiently constructive in polytime. And our work uses multiple results, ideas from previous work, which I'll talk about. So these are our results. So in the remaining 5 or so minutes, I just want to sketch what we have for EF1. Right? So I'm going to show the price of EF1 is order of square root n for normalized, for scaled valuations, as I mentioned earlier. There are 3 ingredients which go into this. Firstly, there's this algorithm by Lipton, Matakis, Mehta, and Saberi, which I'm going to call the MMS algorithm. Secondly, we're going to look at the case of unscaled valuations and give an order of n, a weaker bound on the price of EF1. And we'll use these two to get the order of square root n bound for the price of EF1. I'm going to restrict myself from now on to just additive valuation. Right? The result holds for sub-additive, but let me just restrict myself to additive right now. So before we do all this, let's just remind ourselves of a few things. So we want to show that the price of EF1 is order of square root n. Notationally, we recall that n is the number of agents, m is the number of goods, and g is my set of goods. And I'm going to fix an instance. I'm going to use A star to denote my social welfare maximizing allocation. So AI star is what agent I gets in the social welfare maximizing allocation. And opt is the total value or the social welfare. And then what we want is for every instance with additive scaled valuations to obtain an EF1 allocation A, which has social welfare at least opt by square root n. If you can show this for every instance I, then this will have shown that in the worst case, the price of EF1 is order of square root n. So that's my goal, and these are my 3 steps. So let's jump into it. Let's first talk about the LMMS algorithm. So I won't spell out what the algorithm is, but basically this algorithm extends a partial EF1 allocation to a complete EF1 allocation. What that means is that the input is an EF1 allocation which is partial, which means that if I look at the set of goods assigned, the union of B1 through Bn, this is a subset of the total set of goods. Not all the goods are assigned. And this outputs to me a complete EF1 allocation A. So it's complete. So the union of all the goods assigned to the agents is G, the entire set of goods. Secondly, what this satisfies is that the value that each agent has for the new allocation is at least what she had for the partial allocation. If VI of AI is at least VI of BI. Each agent's value must, cannot decrease. So this basically extends a partial EF1 allocation, and I'm going to use this multiple times. Okay, so that's the first ingredient. The second ingredient, as I said, is going to be the case of unscaled valuations. So here's an algorithm which gives an order of n price of fairness for unscaled valuations, again additive. It's in 2 steps. So in step 1, I'm just going to do a max weight matching. So I'm going to consider this bipartite graph, agents on one side, goods on the other, and an edge between agent I and good G is the valuation that agent I has for good G, right? We sub I of G. This is a complete weighted bipartite graph. Step 1, I just do a max weight matching. Right? Every agent now gets assigned a good. Let's say B is this partial allocation. It's an EF1 allocation because everyone gets a single good. This is a partial EF1 allocation. Now I'm going to use the LMMS algorithm to extend this to a complete allocation. right? So this gives me an EF1 allocation. And what we show, I'm not going to prove this, but what we show is that the resulting allocation A, the social welfare is at least 1 over 2n times the total valuation of all the agents, right, for the entire set of goods. So this is not just opt, right? This is something stronger. So VI of G is the value that agent I has for the entire set of goods. And then, this clearly also gives us the order of n bound for unscaled valuations, because for each agent I, VI of G is at least VI of its optimal allocation AI star. Um, right. So this algorithm gives me an order of n bound for unscaled valuations. It also gives me something else. It also gives me, so let's just consider the case of scaled valuations now. For scaled valuations, every agent has the same value for the entire bundle. So if I plug that into the inequality shown in the theorem, this gives me that I get an allocation. The theorem gives me an allocation where the social welfare is at least 1/2. What this means is that if opt is outmost square root n, then this already gives me uh, um, a square root n approximation to opt. So the only case I have to worry about now is the case where opt is strictly greater than, let's say, 4 square root n. Right? So this is step 2. Okay, so now let's look at the case of scale valuations where opt is large. And this is going to be in 3 steps. There's a matching step, there's a sequence of exchange steps, and there's an extend step. And again, let's just jump into it. So here's what I do in the matching step. So the matching step, I start off with the social welfare maximizing allocation A star. Right? So this is easily computed. For additive valuations, it's easily computed. And let's say, so let's look at the case. So this example looks at the case of identical valuations. And let's say this is what A star looks like. I'm going to arrange all the goods in a line so that each AI star is a connected component in this graph, is a connected subgraph of this graph. Right? So AI star consists of goods in a segment. Now for the matching, I'm going to match each agent to the good in AI star, which has the most value for her. So this is my allocation B. This is again an EF1 allocation because everyone has a single good assigned to her. Right? So B sub I is agent I's most valued good in her optimal bundle AI star. This is the matching step. Now in the exchange step, I'm going to allow every agent I to exchange her bundle for a minimal connected segment which has larger value. In particular, so while there exists a segment S in agent I where agent I prefers the segment S to what she currently has, I'm going to look at a minimal segment of S which is preferred by some agent J, and I'm going to allow agent J to take that segment and give up what she currently has. So let's just see how this goes. So what this will give us is that, because I'm looking at minimal segments, nobody wants a smaller set of goods. Therefore, this is going to be an EF1 allocation, right? And every agent takes a connected subgraph, takes a segment. Therefore, both of these statements are going to hold. B is always going to be an EF1 allocation, and every agent always has a connected subgraph, right? So let's say that the red agent prefers this segment. However, this is not minimal. There's a smaller segment that the blue agent prefers, so I allow agent A to switch her allocation. Similarly, the green agent prefers this segment. This is minimal, so I allow her to switch, and so on. So this goes on, and let's say that this is what we end up with. And basically, after the exchange step, two properties hold. Firstly, the allocation is a partial EF1 allocation where every agent has a connected subgraph. Secondly, no agent prefers an unallocated subsegment to her own allocation. Otherwise, we would still be doing the exchange step. So at the end of exchange steps, I have a partial EF1 allocation. Then I just do the extend step where I use the LMMS algorithm to extend this to a complete EF1 allocation. Right? This is what I get. So the theorem statement basically says that the allocation I get is a square root n approximation to opt. Right? So this gives me what I want. And this is actually inspired by an algorithm for cake cutting, where I insist that every agent gets a contiguous allocation. Right? And you can see the similarities. Every agent over here is, at least up to the exchange step, is getting a contiguous portion of the segment of this line. Okay, so these are the 3 steps. I've defined the algorithm. I'm sorry it was a little fast. The MMS algorithm it's considerably more complicated. There are a few similarities, but I won't get into that. Please read the paper and talk to any of us. This is a restatement of our results. Uh, okay, so to end with some open questions. Firstly, as I said, so we look at half MMS, but we know that a 3/4 MMS exists. So can we do anything for C greater than half? Or for submodel evaluations, any constancy? What can we say about that? We know that EF1 plus PO allocations exist. What can we say about such allocations? And lastly, what about other contexts such as voting or matching? There can we, how does one formalize the price of fairness? How does one obtain bounds? There are a lot of open questions over there as well. But let me just stop here and say thank you.